All right, let's dive right in. We're going to tackle one of life's biggest, most fundamental questions, and we're using insights from the brilliant Nobel laureate Venki Ramakrishnan. The question is simple. Why do we die? And, could we one day just choose not to? So, here's our roadmap. First, we'll see why the very definition of death is way fuzzier than you think. Then, we'll get into the nitty-gritty of aging, what's happening inside our cells. We'll look at evolution's kind of cold-hearted plan for us, and then, the exciting part, the quest for immortality and the huge, huge questions that brings up for all of us. You'd think that to understand why we die, we'd at least have a solid handle on what death is. But it turns out, that's where we have to start, because our most basic assumption is built on some pretty shaky ground. I mean, it seems obvious, right? But the actual official moment of death, it's always been a moving target. And what's wild is that it's defined just as much by our latest technology as it is by our biology. Think about it. Just a few generations back, death was pretty straightforward. You'd hold a mirror up to someone's mouth, and if it didn't fog up, well, that was that. But today, we can keep a body's heart and lungs going long after the brain has completely shut down. So we've shifted from these simple signs to this really complex idea of brain death, and that just shows you how blurry the line has become. So, for scientists now, the real moment of death is this. It's when the body just can't operate as a single coordinated system anymore. But here's the crazy part, the big paradox. At the exact moment a person is declared legally dead, most of their cells and organs are still very, very much alive. I mean, that's the whole reason organ donation is even possible. Okay, so how does the body get to that point of no return? Well, it's not like flipping a switch. It's more like a slow-motion cascade, a domino effect of failures at the cellular level that starts, and this is going to surprise you, pretty much the moment we're conceived. Yeah, you heard that right. Aging isn't something that just kicks in when you spot your first gray hair. It is a lifelong process. It's this constant accumulation of tiny bits of damage and little changes that begin before we're even born. It all starts with our core instruction manual, our DNA. Over our lifetime, it just accumulates errors, little typos, and these chemical tags get stuck on it. This is what's called epigenetics. It's not changing the letters in the book. It's more like putting sticky notes all over it that say, read this part or skip this chapter. So what happens when the instructions get all garbled with typos and sticky notes? Well, the stuff you try to build with them starts to fail. Proteins, they're the little workhorses that do literally everything in our cells. They get made incorrectly, or they start to get sticky and clumped together. And that's exactly what you see in diseases like Alzheimer's. And this whole process literally saps our energy. You see, our cells have these little power plants called mitochondria, and over time, they just get less efficient. They start spewing out this damaging exhaust called free radicals. It's kind of like an old car engine. It's a big reason why your grandson can run circles around you all day. His little power plants are just running way cleaner. And this leads to a really interesting paradox. Some of our damaged cells go into this state called senescence. Now, they stop dividing, which is actually great. It's an anti-cancer mechanism when we're young. But the problem is, they don't die. They just hang around like zombies, pumping out these signals that cause inflammation. They're basically screaming, hey, there's a problem here, and calling in the cavalry for a battle that never ends. So you can see how this all connects. It's not one thing. It's a cascade. The DNA gets damaged, which leads to faulty proteins. That messes with our energy supply from the mitochondria. This then leads to these zombie cells building up and causing inflammation, which ultimately results in the organ damage we call old age. All right, so this brings up a huge question. If our bodies are so obviously prone to breaking down in all these ways, why on earth didn't evolution just give us better repair systems that last a lifetime? And here is the absolute key, the cold, hard truth. Evolution is completely 100% indifferent to how long you live. It has only one goal, and that's fitness. And in biology, fitness means one thing and one thing only: your ability to pass your genes on to the next generation. That's it. Full stop. Just look at the animal kingdom. A species' lifespan is a perfect reflection of its environment. For a mouse, what's the point of having repair genes that could let it live for 40 years if it's almost certainly going to get eaten by a hawk in 2? But a bat? It can fly away from predators, so it's worth it for evolution to invest in a longer, healthier life. So it all comes down to this really cruel trade-off. Evolution will pick traits that help you survive and have kids when you're young, even if those exact same biological processes are going to cause cancer or heart disease later on. Because once you passed on your genes, as far as evolution is concerned, its job is done. So, if aging is just a biological process, a program that's running, can we hack it? Now that we're starting to understand the machinery, can science actually step in and rewrite the code?
Well, people are definitely trying. Researchers are exploring some fascinating and, let's be honest, sometimes super hyped ideas. Things like using special proteins to basically turn back the clock on a cell and make it young again, or studying what happens when you introduce factors from young blood into an older system. And of course, the big one, caloric restriction.
And that right there is the billion-dollar question, isn't it? This drives so much research. Can we somehow trick our bodies into activating all those amazing longevity pathways that fasting triggers, but without actually having to, stop eating? Can we have our cake and live longer too? The answer is maybe. There are drugs out there, like rapamycin, which was first found in the dirt on Easter Island, of all places, that can mimic some of those effects. But here's the catch. It's also a powerful drug that suppresses your immune system. So the huge challenge is figuring out how to get the anti-aging benefits without all the dangerous side effects. Okay, but let's just imagine for a second. Let's say we do it. Science succeeds, and we invent a pill that safely gives everyone an extra 10, 20, 50 years of healthy life. What would that world actually look like? This is where we run into a massive conflict. Because if you were offered that pill, let's be real, almost every single one of us would take it in a heartbeat. But what we all want as individuals could, ironically, create a society that's less dynamic, less creative, maybe even stagnant. Just think about it for a second. With very little turnover between generations, the older folks would just continue to accumulate wealth and power and influence. But if you look at history, real progress in science, in art, and everything, it's so often driven by fresh, new perspectives from the young. An ageless society might just risk losing that incredible engine of innovation. And that really leaves us with the ultimate question. So many philosophers and thinkers have argued that it's the knowledge that our time is limited that gives us the drive to do things, to create, to love, to make our mark. So if we erase that finish line, do we end up losing the very motivation that makes the race of life worth running in the first place?